for putting together this workshop. I know it's a lot of work, even to do small workshops like this. Last year we organized one here. And even with the great support of the Institute teams, it's a lot of work for the organizers. So I'm very grateful for them to have made this happen. What I want to show you today, or to present to you today, is a new formalism that we've been developing in the past few years to describe statistics of fluctuation in complex systems of a particular nature that I will describe later. But before I start, let me acknowledge my collaborators. Most of the theoretical work, actually the work began with the PhD thesis of Domingos Salazar, who is now a professor at another university in Recife. And more recently, we expanded the theory we started with Domingos with the help of Antonio Murillo. Here's some experimental colleagues of mine from Recife who provided us with some data, and we collaborate in a particular application of the formalism that I'll show you later. Anderson is the leading professor there in the optics group. There are other colleagues, but too many to mention in the first slide. And my students and postdocs who have been contributing in different ways, different parts of this work. So, so what's the problem I want to discuss today? Let me tell you first that I'm not interested in any specific problem in particular. I want to develop a general formalism with which I can tackle many problems of, as I said, of a particular nature. And what I mean is fluctuation or fluctuating phenomena in general. So I think everybody in this room knows that Gaussian is a very common, is the normal behavior for simple system. And that's the difference I make between simple and complex. I'll make it more precise later. And we know why Gaussian is so common in nature is because of essentially because of the central limit theorem that says this, as we have been hearing before, some of independent events leading to Gaussian law. But non-Gaussian is actually the norm in complex systems. Most of complex systems, at least the ones we are interested in, show a non-Gaussian effect, or non-Gaussian effects. And the one that is a prototypical non-Gaussian system for us here is turbulence. So if you look at his histogram, or this velocity distribution, or actually velocity increment. So this is the velocity increment, the difference in velocity between 2 points, 2 nearby points. That's the probability of finding this velocity fluctuation. And when you look at large scale, large separation, you see this Gaussian behavior down below here. The curves have been shifted just for presentation purposes. And when you go to small scales, when the points are very close together, then you see this distinctive heavy-tailed behavior. So that's the kind of system we want to describe. Of course, you see many systems in financial markets, in social problems, and many other systems. So the question I want to address here is how do these heavy-tailed distributions come about? How do they appear from a more physical standpoint? I guess everybody in this room has a good answer for this question. Oh. But my task here is try to convince you that I have a better answer, at least for the kind of systems I have in mind. So when you mention heavy-tailed distribution, the first thing that comes to our mind probably is the power law distribution, particularly the Levy distributions, which has this unphysical property that the variance is infinite. So that's a bit disturbing. So I call this an unphysical property. There's another way to generate non-Gaussian laws or non-Gaussian statistics is if you compound two different statistics, and if you choose them properly, you get pretty much any distribution you want. And that also more recently has been known as the name of superstatistics. The problem is that you have to pretty much prescribe a priori what the two distributions you want. Say you want a Gaussian and you average that Gaussian with a weighting distribution that you have to prescribe a priori, there's essentially no physical model to suggest in this view. That's more a heuristic approach, how to choose the distribution. So that's what our formalism comes about. It's a way to guide you through this process of generating non-Gaussian laws that they are suitable for this kind of system. Something wrong there. Okay. So that's the outline of the talk. I want to describe the theoretical framework for our theoretical framework to deal with these problems. And then I'll briefly mention a list of applications that I've been working on recently and make very brief conclusions. I have always 2 points. Okay, so that's just to put things in perspective. I'm interested in systems, what we call hierarchical systems. So fluctuation in systems which have many different scales, time and length scales. So they usually, when you have hierarchical systems, usually you find power law behavior, or at least some heavy-tailed behavior, non-Gaussian tails. So that's the kind of system we are interested to, or that we want to model. And turbulence, for me, is the prototypical mode-scale phenomenon, maybe one of the most important ones. When you know, the turbulence is characterized by multiple spatial and temporal scales, and that's a nice picture that shows that. You see these large edges. You have edges of maybe 100 kilometers of magnitude, maybe 1,000 kilometers if you come. And then when you come down to, if you go to the beach, to the ocean, you see edges of meter order of magnitude. So it's a very huge span of time and space scales. So we want to deal with this kind of system. I always have to point that way, sorry. And in turbulence in particular, there's a particular, it's known that what drives the turbulent flow is the so-called energy cascade. When you force this, of course, it's a Newtonian fluid, so it's a dissipative system. If you want to keep the turbulent state, you have to feed energy into the system. So you inject energy in the large scale. It's barely, oops, sorry. This is really annoying. Yeah, you inject energy at the large scale, and then this becomes unstable. You get these edges, large edges that break into smaller edges and break into smaller edges until it comes down to very fine scales, and when the kinetic energy is dissipated into heat. So that's a usual picture of the energy cascade put forward by Richardson. But that's not new. Of course, Leonardo da Vinci already knew this phenomenon, and he gave a very accurate description of this energy cascade, of course, not with this notation or nomenclature. But the one thing that's important here to remember that he said that large things are rotated only by large edges and not by small ones. So the small edges don't act back upon to the large edges, but the small things are turned by small and large edges. So that's important when you try to quantify this cascade. So the first quantitative description of the energy cascade was Kolmogorov's theory. And that's just a sketch of the main ideas in his approach. And here again is the cartoon of energy cascade. You inject energy at the mean flow. The flow becomes unstable, generate edges that themselves are unstable and then break into smaller edges all the way back, all the way down to the smallest scale, and it gets dissipated into heat by viscous force. But on this cascade, the kinetic energy is pretty much cascaded down without dissipation. So you have the so-called integral scale for the energy cascade. So the way that he essentially described this process is by, well, you have energy injected at the large scale, and then you have energy flux for the next scale, and then another energy flux to the next scale, and so on and so forth until dissipation. Now, if you assume that this energy flux, that's actually he used the energy dissipation rate, but I'm going to use the rate of energy transfer between levels or between scales. So if these fluxes were constant, then the fluctuation, the probability of finding a particular value for the velocity increment would be a Gaussian, where the variance here can be associated with this energy flux. But of course, as soon as he published this or he discussed this, Landau criticized his model because it does not take into account intermittency, the fact that you have this energy burst at some point. And so he later, after the war, he corrected the theory and now assumed that this energy flux fluctuate. They are not constant, but they themselves are random variables. They fluctuate, so that gives rise to the intermittence. And he prescribed a particular way how they are distributed. He used the log normal model, which you now know that's not the best model for that. So the question I want to describe first is how to model the fluctuation of this hierarchical energy flux. And here is our model. I have to try to go faster now. So of course, I'm going to use a stochastic dynamics. Now, what else? No, if it's a stochastic process. So I write down this Langevin equation, or stochastic differential equation. Now this is Wiener process. We have an introduction to stochastic calculus before, so I don't need to explain how to interpret this equation. But what's important here is that you have this deterministic coupling, and then the multiplicative noise. That's the intermittence noise. If you kill the noise for the time being, forget this, you just have a linear system a system of linear ODEs. They all relax, so they are all coupled. The important thing is that at any level, you are only coupled to the flux rate at the level above. So it means that you only have local interaction. So that's the nature of the cascade, the hierarchical structure, if you will. If you kill this, then you see they all relax to a constant value, so you don't have fluctuation. That would be K41, Kolmogorov's initial model. So you do need this noise term to generate fluctuation. And if we impose now that this, so the equilibrium condition that on average, they should have the same flux, which is the flux that you inject at the larger scale, pretty much it takes that you only have this linear term. It's like the Newton's law of cooling. So that is, and now if you want invariance on the change of scale, if you just change the scale of your energy, this shouldn't change the equation, the dynamics. So see, you can only have these power laws here, these binomial terms here. And that the multiplicative noise should be 0 when the flux is 0. So that guarantees that the probability never goes to, so this quantity never goes to 0. So that's some technical remarks. Now, how do we solve that? Let me just write down this equation in full so you can see that I do have a hierarchical system of SDEs. And I'm going to assume, which is pretty much the case in turbulence, but also in, I think, most systems which have hierarchical structure, that the dynamics are really separated apart in time. So the smaller, the faster the dynamics. So these are the low variables. Those are the faster variables down here. And if you separate, so gamma sets the time scale for this relaxation. So if you organize them from slower to faster, then I can solve this by, you freeze one, solve the Fokker-Planck equation for this particular level. It depends only on this parameter. And then you solve another one, holding the other variable fixed. And then you have this conditional distribution for each level, holding the value of the energy flux above it constant. And then you solve this by Fokker-Planck, you integrate this, and some miracle happens. The first thing I need to tell you is that because I'm going to solve Fokker-Planck equation, I want to have linear analyticity. So the terms in my Fokker-Planck equation should be analytic. And from that kind of noise, you only have two options. One, S, that parameter S, that's dictates the shape. Dictates the shape of the noise here. Can only be either one. Can only be either one. So we have a linear noise, or 1/2, you have a square root. And when you do those integrates, as I told you, then you have two functions for the distribution of that the fluctuating variable at the smallest scale, the lowest level in your hierarchy. There's some Maya G function, so some special function. I don't think you have heard of it before, probably, or not many of you, but it's just special function for our purpose. But you have an analytic solution for that set of ODs within those approximations. Now, what we want is the velocity distribution in our particular problem, or the distribution of the fluctuating quantity, the quantity that you measure. So this is just the background that on top of which the quantity is evolving. So in the case of turbulence, you measure velocity, and then the tip, if you just put a probe here and measure the velocity, that's the kind of signal you would measure. And the way we deal with it is that you say that, well, locally, for a short time, the probability distribution is a Gaussian for a short time. But now, over a long span of time, this quantity epsilon, with the energy dissipation, the flux rate, whatever, it varies. So if you want to get the marginal distribution, you have to average over all possible values of this variance, if you will. So, but now that's why I had this long discussion how to compute this. We have those G functions here. If you insert this in here, then what you get is another G functions. They have wonderful functions to work with. They have wonderful properties. But again, the probability of your signal is now given explicitly by a G function. And remember, it's the number of levels. How many different time scales you have in your system. In this class, SCO1s, you can show that this has a power law decay. But the other class, that's the linear multiplicative noise, if you will. Whatever the square root noise gives you you can see, but this is the tail is an exponential x squared raised to some power. So this is a stretch exponential with some power here, which is not important. So you have two different classes, power law or stretch exponential. You only have those. Now, a brief, I insert a few slides because I knew that Mario would be here. So we can try to make a contact between, they are different, but they have some similarities between what he said. We can view this hierarchical system in like you have a system with multiple times or length scale in a thermal equilibrium, in a sense that if you make measurement in a small system, the largest system would act as the heat bath, but this temperature that would characterize the heat bath is itself a fluctuating quantity. The higher structure above it acts as a heat bath for this other system, and so on and so forth. So in the short time scale, you have Boltzmann-Gibbs distribution, but now this beta n, which is the inverse of temperature, fluctuates slowly, and you have to average over all possible beta n's to find your distribution. So the question is how to construct the p beta n. We can do from the stochastic dynamic approach, but you can do, I don't have time to go into the detail, but you can do from a maximum entropy approach. So you just write your entropy. So you have Q variables is like the phase space variables in your system, and all the other variables like the effective degrees of freedom that describe the different scales in your system, you put in this beta. So this is beta, it's a vector beta 1, beta 2 to beta n. So you usually define your usual Gibbs, Boltzmann-Shannon entropy. You have to be careful about how you maximize things, but you can do that. I only want to mention one important thing. That's where you have these two classes, because you have to impose some constraints in your maximization. First one, of course, normalization, but usually you have to hold one of the moments fixed when you do maximization of entropy. And depends on if R is put, so instead of just having, usually you just have the average, so just R equals 1. But you can be more general, so you can, some R moment is fixed. If R is positive, you get one law. If R is negative, you get another law. So what it means that if you fix the average temperature, you get one law. But you fix the average beta, you get a different law for the distribution. And those, they are here. And in the general case, when R is not 1, some more, no, then you get, you solve for the p beta n, but now instead of g function, you get the Fox H functions. When R is 1, R is embedded here in this parameter. When R is 1, you get back the two distribution I had before. So there's some way that you can make this description more formal in a statistical mechanics perspective. So now I want to show you some applications. Okay, the first one, of course, was in turbulence. That's what motivated us at first, but then we realized it's a more general approach. I'll try to convince you that you can deal with many different systems which has the problems that you want, different time scales you can handle with this approach. So there's some data, some experiment done in France by Benoit Chabot and Philippe Rocher. They were very kind to provide us with the data. They just measure, it's a helium jet gas flow, and they measure the temperature here with a hot wire probe. And we just do the statistics of the fluctuation. So the velocity increment between two consecutive measurements. So it's the same point in space, but you can translate into increment between two nearby points. And that's that's the velocity increment distribution. X now stands for delta V, and that's the probability. And the circles are the data, and you have different curves here for different ends. So remember, n is the number of scales in the system. We don't know in principle how many scales you need, so that's something you need to find from the data, unless you have a model that could tell you how many scales you are supposed to have. So you try different ends. They pretty much give the same. They give good description, but then you have to be more careful to say what's the best n for the model. And how many scales do I think that are present in the system, at least that I need. And another thing that you have to realize that if you go back to the model, it gives you more than just the distribution. Just go back here. It gives more than the distribution of the signal. It gives you the distribution of this, essentially the variance of the signal. So what you can do, you can construct a series of the variance and try to fit with those formulas. So now you have two, here. You have two series that you can fit. So this is just what you call the background distribution. That's epsilon you can see, but that's epsilon, that's probability of finding a given epsilon. So essentially you construct a series of variants. I can give you details. But then you fit with those functions, and you see that n equals 1 is not a good fit, n equals 2 is not a good fit, 3 is getting better, but it's still not good, and then you keep going until n equals 7, then you get a pretty decent fit for the variance. And when you look, so you extract there's a parameter here that I didn't mention. There's one beta parameter in the distribution. So some parameter that you extract from here, put in the other formula for the p of x, for the signal, and when you look here, the red curve gives you a very good adjustment of the data. So now you have two data that you have to fit, and for each of them you have an analytic solution. So that's why it's a more stringent test for the model. Okay, and the next one is now financial. There's always this. I'm sure you have heard. There's an analogy between financial market and turbulence in fluids. We all know when the market is turbulent, it means that it fluctuates a lot, and you can make a more quantitative analogy. So instead of an energy cascade, we have now information cascade. So information cascades now from larger to a smaller scale, which means that they have different. So the investors in the stock market say different investors have different horizon of investment. So you can look at what's going to happen 1 year from now and make your bets or your investments. You can look what's going to happen 1 month, 1 day, and even the tick, the so-called intraday investment. So you have now this cascade of information from larger to a smaller time scale. And eventually, this information gets destroyed here. Nobody uses it anymore. So that's the analog of dissipation. So by the reasons I gave you, you should expect that there's a quantity that measures this information cascade. That's what we call the volatility. It's the amount of uncertainty you know about the future. So that's essentially the lack of information is expressed by this volatility, and there's a cascade down as before. So just build up the same type of model. By the same reason, there is only two classes. And again, you have the local equilibrium. So in short time scale, things should be Gaussian, but over longer time scale, you have to average over your Gaussian distribution. And because you have the same model, you have the same two classes of distribution, power law and stretch exponential. And you have to see which one fits the data better. And again, here's the power law. And in this case, you do the same. That's the variance. You construct a series of variance from the price. That's the price distribution. The price increment is called the return. You can get your variance here. That's the distribution of your variance. And you have to do the same trick. And here it seems that n equals 3 gives a better, it's like we call a better joint adjustment of the two curves. So that's how you select the scale. A more recent application, a very interesting one, surprising one actually for us, was to apply this theory to random lasers. I don't know if you ever heard of random lasers, but if you are in Recife, you'll hear a lot about it, because one of them was this, well, one of my collaborators, Anders, was here, was part of the group that discovered random lasers some 20 years ago or so. And they were the first one to build the so-called random fiber laser. There's a random laser that works in a fiber, optical fibers. That's your fiber. You have a core, and you have erbium ions. So that's your active medium, if you want. But they put it in a heterogeneous way. So you have a random, on top of the erbium, you have a random array of scatters. So light is a scatter at random, and so it's a laser without cavities, so you don't have a feedback loop by the mirrors. So it's just you have multiple scattering of the photons. Eventually, you get a feedback loop, and the thing starts to laser. But the thing is that when it lasers, the intensity is not constant as in this laser. It's pretty much constant over time. In random lasers, every time you measure, you find a different intensity. So that's what they do. They did the experiment. They acquired by our requests, because you need to remember what I'm trying to, one of the things I'm trying to model here and to detect is what the shape of the tail. Is it a power law? Is it a stretch exponential? Is it just a simple exponential? Those are very difficult questions to answer with a finite amount of data. So at least to have a good description, we need a lot of data. So usually they do 1,000 spectra. We ask them to do at least 100,000 spectra. So that's take a spectra of your laser, just put this in an analyzer, and this is, I'm going to have 1,000 here just to show, and you take the maximum of each spectra, so that's the intensity. And here is how the 150,000 spectra looks like. That's the intensity as a function of time. That's before the laser threshold, just near the laser threshold and above threshold. So you see there's a different change, quite significant change in behavior. So we wanted to describe that as something interesting happening. And what was known before was that before the threshold, before you just have a spontaneous emission, essentially. So the fluctuations are essentially of a Gaussian nature. So if you look, now we look not at the intensity of the light, of the spectrum, but the intensity fluctuation because of the analogy with turbulence. What's important is the velocity increment. So here look at intensity increments. And you'd see that before fluctuation is essentially random. So this is a white noise. So it's a random distribution. Now, when you are near threshold and above threshold, the situation changes completely. In near threshold, you see that's the intensity increments as a function of time, and here the statistics of it, and you see there's a long tail and this peak in the center. And because of that, we need to combine now two. We did what we call a statistical mixture of two of those distributions. And so instead of just one, they're still G functions, but you have two of them. So they capture, one captures this and the other one captures that. And this is a stretch exponential class, no longer the power law. And that's above threshold. You see they have an even longer tail. And in this case, I forgot to mention, just n equals 1 would be enough to describe the data. But here, well above threshold, you need at least n equals 6 to give a very good description of the signal itself and of its variance. So that's an indication that when you're above threshold, there's a lot of the equivalent of eddies in this photon doing some feedback loops of different scales. So that's our interpretation. But there's an evidence that the system has different time scales. Briefly, I'm running out of time. That's a very recent work, and that's a very not impressive result, at least for me. We went back to that data, turbulence data from the French group. Now, in turbulence, it's known that the velocity distribution is actually asymmetric. The ones I showed you before were symmetrized, because if you have Gaussian with zero mean, and you average over Gaussian, symmetrical Gaussians, you get symmetrical distribution. But the actual distribution are clearly asymmetric, and it follows from Kolmogorov's 4/5 law. But it doesn't matter. So you can see that you have a longer tail here, heavier tail if you want, a shorter tail or less heavy tail here. And we are able to construct from this model a symmetric distribution. But now the price you pay is that you have now this Fox age function of two variables. But you can show, but the interesting, everything is explicit analytic. And what you can show that, say in this case, you have a power law on this tail on the left-hand side for negative values, and you have an exponential behavior for at least the power law tail now gets an exponential cutoff. So that's, you see that you have different tails on different sides, and that follows from, I can give you the details of. I have to be close. Okay, to conclude, of course, you can do a quantum version of this. I can discuss with you. Mario later can do, instead of using your Gibbs distribution, you can use the quasi-probability distribution, the Wigner function, and you suppose you have a hierarchical structure. You average over, and lo and behold, you get a G function, either for the Wigner representation or the Husimi representation. So you have a classical and quantum theory for hierarchical systems. So we are looking for particular systems for data to apply this quantum systems when we can apply this technique. Okay, so in conclusion, I tried to present you a general unified description of fluctuating phenomena, as I said, both in classical and quantum contexts. In any case, you always have two universality class because of the reasons I mentioned. Either you get power law behavior, or you get stretch exponential. The good thing is that everything is analytical. You get all the distribution in an explicit formula, and you can then apply to your system, to your data. And I said there's a great potential for application. We have already checked in turbulence, financial market, random lasers. We are trying to collaborate with people in London to get data from their quantum optics to see if you can try that. I didn't mention, but we can do anomalous diffusion in a hierarchical system. We are looking for application in biology. I've been trying to talk to Mauro Copelli to see if we can apply to some of his systems. And I think there's application in many other systems. So if you are interested, please, I would be very interested to talk about possible applications. Okay, and with that, I conclude. Thank you very much.